Hello. We have been studying the consequences of an electron moving in a periodic potential, and we used a theorem called Bloch theorem to show that the wave function should have a particular form, that it is if you translate by a Bravais lattice vector, the wave function picks up only a phase which is e to the power I k dot r, where r is that Bravais lattice vector. So, this was this led us to the formation of bands, and as I showed, the bands for example, the band formation means that you have in one dimension, for example, your energy is epsilon 0 minus twice t cosine some k times. If I put the a explicitly, the lattice constant, then it will be k a, where k takes some discrete values depending on the periodic boundary condition or open boundary condition that you use. So, for example, k in one case is some 2 m pi by n and so on. So, that is that is the solution that we actually wrote down. So, that the band, then suppose I set epsilon equal to 0, then this band goes from minus plus 2 t to minus 2 t with n states in between. Each state can take care of 2 electrons. So, can accommodate 2 electrons, and that means that if you are at half filling, then your Fermi surface will be at a Fermi level will be at the middle of the band. So, for example, this kind of a band will look like from minus pi by a to pi by a. This will be like this. So, this will be minus 2 t, this level will be minus 2 t, and this will be at plus 2 t. Okay. So, that is the solution, and you have to put in a large number of n number of energy levels in between. And so on. Now, depending on your filling, suppose you are half filled. So, you will only fill up half the number of states, and your Fermi level will be somewhere here E f. Now, remember, this is a E versus k graph. So, this is E versus k graph, and this is one dimension, and this one has a Fermi level is at E f. So, where is the Fermi surface? Now, in any dimension d, a surface has a dimension d minus 1. Okay. So, in one dimension, the surface will be basically 0 dimensional. So, d equal to 1, the surface is 0 dimensional. Okay. So, this 0 dimensional surface means it is basically a point, and you can identify those 2 points. Those 2 points are these points, this point and this point. So, these are the so called Fermi surfaces or Fermi points in a one dimensional tight binding model for half filling. As you increase the filling, the point will move up, it might come here, or if you are reducing the number of electrons, you are going to lower fillings, then it will be somewhere here or here and here and here and here. So, there will always be these 2 points where the constant energy line, which is a line here, which is a surface in here in d dimension, any d more than So this is so this constant energy surface, so called constant energy surface, is a set of 2 points in this d equal to 1 dimensional problem. Any finite dimension, of course, d equal to 2, that will be a line, d equal to 3, that will be a surface as we know it, 2 dimensional surface, and so on. So let me just illustrate this again with a by showing the Fermi surface, for example, in a case which is very well known, and for example, this the 2 dimensional. So let me just show you the Fermi surface in the 2 dimensional case. This is what we have been doing. So this, for example, is the Brillouin zone for a square lattice, this left hand side. Okay. Now this Brillouin zone basically implies that my states that I will calculate will fill it in. So let me show you what a 2 dimensional energy spectrum will look like in tight binding model. It is very straightforward actually, knowing the 1 dimensional. Suppose you have a square, so a square is an ideal example where the 2 directions are orthogonal to each other. So if you draw a reciprocal lattice, that will also be a square. So then there will be a kx and ky, these are orthogonal, and the spectrum, that means this spectrum will just be a set of 1 dimensional spectrum in each dimension. So what does that mean? It means E as a function of k is again some epsilon naught minus 2 t cosine kx into a plus cosine ky into a. Now of course I could choose a and b as 2 different lattice constants in the 2 directions. That would just make this will be just a b then. If you had a in this direction, lattice constant a in this direction and b in this direction, sorry, b in this direction, then there will be cos kx into a plus cos ky into b. In a square lattice, of course, a equal to b. So that is why I wrote kx a plus cos ky b. So in 3 dimension, for example, this will be just epsilon. So this will be E 2 d in tight binding, nearest neighbor tight binding. So in 3D, it will be similarly E some E0 minus twice t cosine kx a plus cosine ky. Say this is all lattice constants in all directions are the same. So ky a plus cos kz a. Otherwise, I will write a, b and c if the lattice constants are different. This is for a cubic lattice. For any d dimensional lattice, lattice of this kind, this is called the hypercubic lattice. You can generalize this lattice a square to cube to a cube in any dimension, in d dimension. So that will be like minus twice t basically sum over alpha cosine kx k alpha into a, if all the dimensions are the same, that is constants along all the dimensions are the same. So this alpha will go from 1 to the number of dimensions. So that is the spectrum. So it is actually very straightforward for cubic lattice to do it. For one triangular lattice or FCC or BC, that kind of lattices is more complicated, but it is still doable. All you will have will be, there will be cross terms between kx, ky and so on. Cos kx into cos ky kind of terms will appear with suitable form factors like root 3 by 2 in for triangular lattice and so on. So, that is just a technical detail, but for a square and cubic or even one dimensional lattice, this is absolutely straightforward, and what I am writing down is just a generalization of the one dimensional problem into 2, 3 and higher dimension for hypercubic lattices. So, now let us just concentrate on the two dimensions, this one, the 2 dimension. Now, I have of course a kx ky surface. So, that means my plot E versus k will be a 2 dimensional plot. Okay. So, let me draw it with black. It is a 2 dimensional plot. So, this is kx, this is ky, and this is E energy, and epsilon naught I again take to be 0. So, in that case you can easily see that this will be like a bell, but now in 2 dimensions. It is a 2 dimensional surface. So, it is like one dimensional surface rotated like a bell along this z axis. So, then of course, if I draw a Fermi a constant surface here, which is for example, so this is a constant surface. If I draw, this is a surface of constant energy, because it intercepts this axis at a particular point, energy axis, and it's horizontal. So, this energy surface cuts this bell kind of structure, inverted bell kind of structure at points which are along the surface of it. So, then of course, for tight binding model we can determine exactly how that surface looks like. So, that is what one let me just show you here. For example, this is the first Brillouin zone. So, let us just write, as I said that I can reduce everything into the first Brillouin zone. So, my band structure basically is I will draw only in the first Brillouin zone, and the example that I have given, I have only one orbital. So, I will be living in the first Brillouin zone only. So, let us just plot the so this is kx ky. Now, of course, you have pi by a, minus pi by a, and then you have plus pi by a along a y direction and minus pi by a along k y direction as well. And if you look at your Brillouin zone, this is this is your Brillouin zone. So, now you have to fill up this Brillouin zone. Depending on the number of electrons, you will basically fill, and you will find, for example, if you have a very low filling, then your Fermi surface will look like a circle around this gamma point. This point is the gamma point, central point. As you increase, you start filling up the Brillouin zone, and so that's how the Fermi surface will look like. I mean, it will become more like this as you increase the filling and so on. So, that's so that surface, that red surface is the region that is filled in is this. These are the states which are filled out. If you increase the chemical potential, if you increase the filling, the number of electrons, density of electrons, then it will increase to this one, and so on and so forth. It just keeps on increasing. So, that's how the Fermi surface is plotted. So, I will at some point show you some band structure and some Fermi surfaces that are for real materials. Of course, in 3 dimensional real materials it is much more complicated, but we will demonstrate some of this, but for the time being let me ask you to at least do it yourself. For the one dimensional case, find out the two Fermi points. Here it will be Fermi lines, remember this is just a line, the outer, the so called outer surface, this surface is a line here. So, d equal to 2, so the surface has a dimension 1. So, this is the line that I am talking about. This is for lower filling, the line is almost like a circle, the periphery of a circle. The inner region of that is filled up. So, that is the highest occupied energy surface in the d dimensional plane, which is d, which has the dimension of d minus 1. The surface has the dimension d minus 1. Okay. So, this is how Fermi surfaces are drawn, and this is how the band structure. Once you do the band structure, then the procedure is very simple. Once you do the band structure calculation, you have this set of energy levels. For example, in 2 dimension it goes from minus 40 to plus 40. You can check it. See, in 1 dimension it goes for from minus 2t to plus t. In 2 dimension there is another cos k added to it. So, it will go from minus 40 to plus 40, and then see epsilon equal to epsilon naught is 0 still assumed here. So, my 0 is somewhere here. So, around 0 it will be symmetric. If epsilon naught is, if you want to insist on taking epsilon naught, you have to just shift this band structure that much above or below, depending on epsilon naught is positive or negative. Now, the point that I am trying to make is that the prescription is now very simple. These are the 1 electron levels, and you suppose you have n number of electrons. So, you start filling up from the bottom and go ahead, do it, 2 electrons per state, and go ahead and do it, and then you will find the highest occupied energy level is your Fermi level. That is the Fermi level, that is called Fermi level, that is an energy, and if you cut your band structure, this one for example, at that energy, then you will find the surface. So, that is the surface in here, which is a line. That surface is a line in this figure. For example, in the bottom figure, it just is this line, outer line of the red part, the bounding line. So, of the field part of the Brillouin zone. So, that is how one actually does. It is very simple. The prescription is extremely simple, and this is how band structure and band filling and Fermi surface determination are always done. Of course, there are experiments which are very powerful experiments, which do the band structure, which calculate, which not only can find out the band structure, particularly near the Fermi surface, near the Fermi level, and there are also methods which employ strong magnetic field at low temperatures to find out the Fermi surface. So, those are methods that are experimental methods to determine the Fermi surface of a material. If you can look up any solid state physics books, then you will find these methods are described, and they are very powerful methods to describe, to find out the Fermi level, the energy bands close to Fermi level, and the Fermi surface. The interesting thing is that for an insulator, of course, there is no Fermi surface, because there is a gap. So, the highest occupied level in an intrinsic semiconductor, for example, will be at the midway between the midway of the gap. So, there are no states there. So, there is no Fermi surface to talk about. Okay. So, let me show you some band structure, real band structures, which are here. For example, this is for as I said, for graphene the band structure requires you to go to a lattice with a basis. So, there the band structure is fairly interesting and complicated in the sense that look at the 3 dimensional figure. This is again you can see the same figure that I have drawn on the right hand side here. It is not identical, but it is the same principle that one has used, k x on one axis, k y on the other axis, and so this is k x axis, this is k y axis, and then energy is along this third direction z direction. And remember I mentioned that there are directions here along which one generally plots the band structure. So, the gamma is the central point, k x equal to k y equal to 0, and there are these special points, symmetry points called k, k prime and m, and look at the band structure. K and at k and k prime, the upper band, and there are 2 bands, because there are, remember, the unit cell has 2 atoms and these atoms are inequivalent, although they are both carbon, but they are inequivalent in the sense that the view of the lattice, as I said, from these 2 are different. So, they are not equivalent in terms of symmetry. So, there will be then 2 bands, there will be twice the number of bands as we twice the number of states as we did in this our example. So, that means if we had only single atom in the unit cell, we would have some n number of states coming from the n number of sites, if only one orbital was considered per site. Now, even if you consider one orbital per site, for these 2 inequivalent sites will give 2 orbitals per unit cell, and that will lead to 2n number of states. So, 2 different bands will now appear, and so that is what is being shown here. So, close to Fermi level, this is what happens, that there are these 2 bands, and these bands touch at this point k prime and k, and these are as written, these are called Dirac points, and this has a significance, because if you remember quantum mechanics, then and relativity of course, then you know that in relativistic physics the spectrum E goes as k, not k square. So, that means the equation in quantum mechanics that governs these relativistic particles is called the Dirac equation, as it is just the counterpart of Schrodinger equation, which is the non-relativistic equation for the for quantum mechanical particles. So, for relativistic cases, the corresponding equation being Dirac equation, one finds a spectrum which is linear in k, and if you have a linear in k spectrum, that is called a Dirac spectrum, and these are the 2 points k and k prime, where one actually finds a linear spectrum. So, that is where the bands will in graphene, the bands will be like this, like V kind of structure. So, two bands are meeting here as at a. So, this spectrum, as you can see, is like a V. So, let me just draw it again. It will be simply a V kind of structure. And this is the Fermi level. So, that is exactly what is being drawn here. But look at the band structure, at M point there is a gap. So, this is the graphene band structure is rather strange, because you have a Dirac like spectrum at 2 points in the Brillouin zone, and you have a gap at this M point in the Brillouin zone. Remember these points k and k prime are here and m is in the middle. So, the band structure has some peculiarity which is extremely important for the myriads of strange properties that graphene has shown so far. So, it is a single sheet of graphite and it is a honeycomb lattice with only carbon, but the spectrum has led to such beautiful interesting physics that we will that I am basically tempted to show you the spectrum. So, let me just show you one more. So, this is how the this was shown to you already, the left hand top corner. This picture is already there up. The A1 and A2 are written down here, their coordinates are given, the vectors are given. These are the two unit vectors in the real lattice. You can, as I said, you can choose your primitive lattice vectors in any way you want. So, then this is the spectrum, this is the band structure that you will obtain, the lower curve, this one. Okay. So, again remember these points, the gamma, m and k. So, generally the band structure is plotted along certain symmetry direction, which I will just come to in my next lecture.